All right, hello everyone. So, last video, we saw how to solve any nth order linear homogeneous differential equation with constant coefficients. We saw that depending on the nature of the roots, what my portion of the solution because of that those roots or that root is going to look like. So, we constructed this large table covering every single possible case that could that could arise given that we have real coefficients, okay, real coefficients in our differential equation. All right, now, and we also did a couple of problems. We also solved a couple of problems. Where were they? Okay, yeah, these ones. So this video is actually about doing the reverse, some reverse problems where we have the solution or given some hints about the solutions and all, and from there we find out the general solution and also the differential equation. And why I'm doing this is I personally think that doing these developer understanding of these solutions and this general method of solving much more than even actually directly just solving them this way. So I think this is really something that we should do. So now let's get right into this. So first one, I'll start simple. So we have, let's see, a third. Okay, so we are told that there's some third order linear homogeneous ODE with constant coefficients, and it has we are told that e to the minus 2x. Okay, so the function e to the minus 2x, and also the function sine of 3x. These two are solutions to that differential equation. So I'll actually write this down. So this is third order. This is third order, and these two we know for a fact that these two are solutions. Okay, these two are solutions. Now again, it's really just one of the reasons why I'm doing these reverse problems. But one thing is, it really helps us understand better, okay, and comprehend exactly what is the general solution. What how does it look like, and what are and how do we form it from given these sort of hints. The thing is, these are actually not, and should be kind of obvious, these are not the general solution or anything, because they don't have arbitrary constants here, right? So these are not they, even if you add them, obviously it would be a solution. It's not the general solution, and we still have a bit of work. Even if you multiply some constants with them, you're not gonna get the general solution, because it's third order and you only have two solutions here given. That's why what's important is that we pattern match with these forms, these patterns that we found, okay, depending on the nature of the roots, and we see what what the general solution should be. So enough of me blabbering. Let me just explain. So e to the minus 2x is a root. So we know that e to the minus 2x is a root. Okay, so that tells us first, actually, the what we have to do. I'll actually do three problems in total, and for all three of them, what we have to do is find two things: the general solution, okay, the general solution, and the differential equation itself, So coming back to topic, if e to the minus 2x is a root, we at least know for a fact. Okay, so we don't know whether negative 2 from which obviously if this is, sorry, not I mean, if this is solution to my differential equation, we know for a fact that this is a root to my characteristic equation. I don't know, we don't know whether this is repeated or not, don't know anything like that, but at the very least we know that it's a root. Okay, we know that it's a root, and we also know that at the very least c multiplied by some constant c, okay, let's say c1 multiplied by this has to be a solution to my differential equation. Okay, this being homogeneous and linear tells us so. So if I'm trying to form a general solution, it's going to be y equals this portion. For a fact we know that's part of the general solution. What else? Okay, so another interesting thing is we have sine of 3x. Okay, sine of 3x, and this is one of the solutions. Well, the thing is, for these linear homogeneous equations, constant coefficients, or at least for the homogeneous solution, okay, which we're dealing with, the sine term or the cosine term don't actually exist by themselves, or they don't actually just occur by themselves in the general solution, as we saw in this concise form. If you have cosine, okay, if you have cosine, you definitely also have a sine term, okay, And not just that, you're gonna have an exponential term also. It might disappear, okay, and we saw, sometimes it does disappear when, lambda equals 0. Probably that's gonna happen here. But anyways, the most important thing is, sine or cosine, the trig terms definitely don't occur by themselves. If you have one of them, you definitely have the other. So since we have sine, we know for a fact that cosine is there. Also, we see that, it's cosine of mu x and also sine of mu x, though both, the coefficient of x inside these are the same. So, and it's, all this comes from our complex roots, right? Mu is our, the imaginary portion, the imaginary part of our complex roots, from which that solution comes from. So we know for a fact, okay, since sine of 3x is here, one thing is cosine of 3x also has to be there in a general solution. Another thing, from whatever solution this comes from, the imaginary portion of that is 3. So, the root, okay, if I'm talking about that root, okay, from which the solution comes from, this portion right here, it's something, well, let's confirm what the real part is later, but the imaginary part, it's gonna be a pair, so it's plus or minus 3i. Okay, so that aside, so we're gonna have cosine of 3x. Okay, we could think about, okay, so this e to the power negative 2x. I already said that there's no guarantee. We are not sure whether this is a repeated root or not. So you could have c2x e to the power negative 2x. That is possible. We still don't know whether that term exists or not. It could be repeated twice, 3 times. We don't know yet. But let's actually try at, first do what we know. Okay, actually first, write down the things that we know. One thing, we can actually see here is that just sine of 3x, it's just sine of 3x. The exponential term indeed has disappeared. Okay, the e to the lambda x term that's supposed to be multiplied with this, okay, you could have a polynomial too if the complex roots pair is repeated. But anyways, you at least need to have this, but we see that it has disappeared. So it's a fact that lambda is equal to 0. That's why the roots that this comes from, it's 0 plus or minus 3i, 0 plus or minus 3i. So and we can also at the very least say, if you have 0 plus or minus 3i, this root at the very least, if it occurs once, then e to the power lambda was 0, the real portion is 0, so 0x, and this is basically 1, so I don't need to write that. Okay, some constant, I'll say it's c2. Okay, we could have a polynomial again. We could have an entire polynomial. We still don't know whether the complex roots are repeated or not. But okay, I think you see what I'm getting at. At the very least, we know there's some constant c2. This is a minimum. Okay, multiplied by this thing multiplied by cosine of 3x. Okay, that's our imaginary portion. And also we are already told that 3x is a root. So we could just multiply some constant there. Again, don't know whether these two the polynomials will be of the same order, but we don't know whether this is gonna be any higher order, linear or quadratic. We still don't know. Anyways, so sine of 3x, at the very least we know that these two terms have to have this constant at the minimum. Okay, so let's actually write that at the minimum portion and see what happens. Okay, so at the minimum, okay, again I said this could have more, so we just kind of like put that on hold for now. Anyways, let's see, we also have some constant c2. Again, I'll put that on hold for now, but at the very least we know that the portion that I've written has to be a solution. Okay, the portion that I've written has to be a solution. Okay, so up to this much we know that this is all of these contribute to the solution. They are valid portions of the general solution. Okay, I think I've blabbered too much here, but anyways, what am I really getting at here? The thing is, if we just notice, we have already confirmed the existence of three arbitrary constants, 3 unique arbitrary constants. Okay, and that is why we are essentially done. Why? Because this is a third order differential equation. They told us that the differential equation in question has to be a third order. Okay, and a third order is going to give you exactly 3 arbitrary constants. We already found them. That's why we know for a fact that these hypothetical extra terms that we were talking about, in case we had repeated roots, they don't actually exist. Okay, and so our roots are actually not repeated. None of them are actually repeated here. So our general solution is only this much. It's c sub 1 e to the power negative 2x plus c sub 2 cosine of 3x. I already said, the exponential term has disappeared because, the real portion is 0. And you have c3 multiplied by sine of 3x. This is your general solution. This is your general solution for that differential equation question. We're done with one portion. We found the general solution. Now, the next thing we need to do is find the differential equation. That's why I was actually discussing about the roots. Okay, so we already discussed that 0, plus or minus 3y and not repeated. Okay, so there are two roots here, so two roots, and the third one is obviously that real root of ours, which is also distinct. This one is also not repeated, as we saw. So negative 2 is also going to be a root. Negative 2 is also going to be a root. Now, if we remember handy factor theorem that we probably learned a long time ago, if m, if you have a polynomial that has these roots, we know for a fact, okay, so, we know that m plus 3i is a root. So m minus, plus 3i, so m minus 3i. This has to be a factor of that polynomial that we're talking about, right? In our characteristic equation, the left hand side of it, this has to be a factor of that. Our factor theorem tells us so. So that's one factor done. Then you have m, m plus 3i, sorry, m minus 3i is also a root, and for that you have m minus 3i, so it's basically m plus 3i. So m plus 3i, this is also a factor. And also we know that negative 2 is a root, right? Is a root. So m minus negative 2, or it's just m plus 2, this is also a factor. And again, similar logic with the general solution, similar logic with that. We're essentially done here, because we know, a third order ODE is gonna only give, characteristic equation of degree, polynomial of degree 3. Okay, and we already have achieved that. If we multiply all the m's, the highest power here is in fact 3. So we're essentially done here. Now the characteristic equation is gonna be this is equal to 0. We need to find the expanded form of this. So let's see, m plus 2. I'll just keep that for. So m minus 3i plus multiplied by m plus 3i, it's going to be m squared plus 9. Conjugate, multiplying the conjugates. So m squared plus 3 squared. So m squared plus 9, this is equal to 0. Now let's try to multiply. This is short. That's why we can actually do it by hand. The other two problems that I'm gonna do, the polynomials are gonna be rather scary, I think. So anyway, so m multiplied with m cubed, and then you have, m squared is just 2m squared. Then you have 9m, and then you have the constant is 18. The constant is 18 equals 0. Now this is your characteristic equation. We just need to find our, differential equation from this. For that, all that we need to do, we've done this plenty of times. Just need to replace the, powers of m by, the derivatives of those respective orders, same as the power. So m cubed, we replace that by, let's see, the third derivative. Actually, why am I writing it like this? More preferably this, let me write it like that. So 2m squared, you replace that by 2, and then you have m squared. So second derivative of y, then you have 9m, m is replaced by the first derivative, and then you have 18 multiplied by 1, basically, and that 1, that invisible 1 is replaced by the zero derivative, just y. So this is equal to 0. So voila, we have our differential equation 2, as we were aiming for. This is a third order differential equation. Okay, this is third order. All right, now we've solved this question. Let's move to another one. It's actually gonna be much quite a bit harder from this, at least, just from the perspective of the algebra. Anyways, we're told that we have a seventh order. That's already kind of scary. So seventh order differential equation, and if these portions, these functions are are roots, are some of the roots that it has. So one of them is x cubed multiplied by e to the power 4x, and another one is e to the power 2x multiplied by 1 plus cosine of let's see 3x plus sine of 3x. All right, now let's try to find the solution. It's actually just for the sake of understanding, let's say 2 sine of 3x. Okay, 2 sine of 3x. Okay, so the thing is, okay, let's actually discuss what happened. First for this portion, the thing is you have x cubed multiplied by e to the power 4x. If you remember this sort of a thing, some power of x multiplied by e to the power e to the power something. It only happens, it only occurs when we have a repeated real root. Okay, when we have, let's see, a repeated real root. Where is it? So here, okay, so we have a repeated real root, right? So it only happens then. And the power of x, okay, the power of x, or at least the last one, the highest one, okay, it's k minus 1. It's 1 less than the number of times that root is repeated. Okay, we need to be aware of that. It's 1 less than the number of times the root is repeated. We don't know whether this is the highest power that x can go here. Like we cannot be certain yet that, suppose say x to the power 4 multiplied by e to the power 4x, that this is not a root. Okay, but at the very least we know that it goes up to 3. Okay, I'll actually first I'll actually write the roots on the side, and then I'll talk about the general solution now. So we know for a fact that m equals, let's see, and what is the root? Okay, what is that repeated root that we are talking about, that real repeated root? Well, it's just the coefficient of x here, and that's 4, right? So we know for a fact that m is equal to 4. So it's a root, not only a root. Okay, since x goes up to the third power, so x cubed, it's repeated 3 plus 1 or 4 times. Not only is this a root, I'll write this in a different color somewhere. So this has a multiplicity of at least, okay, at least 4. That one's done. So discussing that is done. And if it's the case, we'll now write the portion of the general solution that contributes to. If it at the very least has it's repeated 4 times, and if it goes as far as x cubed, this is not gonna be the only term, right? And even if you just multiply it by a constant here, that's still not going to be the only term. Since we have this, we know that the lower powers definitely are solutions, right? The lower powers of x, okay, same form, but the lower powers all the way up to the the some constant multiplied by your exponential. Those are all roots. Okay, and you're gonna have that polynomial. You can simplify that, write it more concisely as this polynomial, okay, up to your highest power multiplied by your exponential. So at the very least, we know that, okay, where is my problem? At the very least, we know that, okay, so y equals, let's see, some constant c1 plus some constant c2, that's multiplied by x, plus some constant c3. Basically, it's gonna be at the very least your your general cubic, at the very least. Okay, some constant c3 multiplied by x cubed, x squared, plus some constant c4 multiplied by x cubed. Okay, it could have more, okay, possibly more, but at the very least we know that up to this much, this will be a solution. This will be a solution. Also, this whole thing is multiplied by e to the power 4x, same as here. Okay, so this is the portion of the solution that we can guarantee for now. Let's move on to this portion. And in some ways, this is actually written pretty well, written in kind of a tricky way. Okay, now it's kind of bewildering to see, this, 1 plus your cosine and sine terms. So we have before seen that when we have complex roots and all, we can have cosine that it's multiplied by some polynomial if it the roots are repeated. Okay, and sine can also be multiplied by is also multiplied by polynomial. Okay? Same order as the cosine. Okay, again if the roots are in fact repeated. But the thing is, where does this lone constant come here? Okay, in this in this portion, that's only designated for complex roots, or at least that's how we're thinking. Where does this standalone constant come from? Okay, and the thing is, we just need to think about this a bit differently. Okay, so we know that this thing is a root, right? This thing not a root, a solution. Okay, a solution. If that is the case, then let's actually just break this up. Since this is the one that's causing the problem, let's break this up from the trig terms. So this is the same as e to the power 2x multiplied by 1. So this e to the power 2x, and also we have e to the power 2x cosine of 3x plus 2 sine of 3x. Now now things should look much clearer. We actually need to notice some things. One thing is that this solution is actually independent, completely different, separate from this. Okay, this, and this is unrelated to all the complex, all of that in the first place. This is due to a real root. Okay, this solution e to the power 2x, and the plus here is we is only due to the fact that since we are dealing with a linear homogeneous equation. If you have this is a solution and this is a solution, okay, their sum is also a solution. So what's being said here is definitely not invalid. Okay, we're kind of going the reverse way and saying, okay, so so if this sum of functions is a solution, then the individual portions right here, okay, the individual portions right here, they need to be solutions, right? They need to be solutions. Okay, so if that's the case, e to the power 2x is definitely a solution. Is definitely a solution. If that's the case, some constant c. I'll call that. How many constants did we cover so far? Up to c4, right? So I'll call that some constant c5 multiplied by e to the power 2x. So this is definitely a solution. And for that, this comes from a real root. Don't know whether this is repeated or not yet. Actually, I really shouldn't have wrote it here. So kind of lacking space here. Actually, I'll add it here. Okay, I'll add it here. So well, definitely we have this portion. Also, m equals 2. The coefficient here. So m equals 2. That's all in. That's also root. Might be repeated. Might not. We don't know yet. Okay, so that one's done. Also, we have this portion of the root, right? Of the solution. Right? We have this portion of the solution, and this is definitely looks like this is due to some complex roots. And one thing might just appear a bit disturbing. It's cosine of 3x, but we have 2 sine of 3x. But again, we just need to remember that our general solution kind of looks something like this: e to the power lambda x, and just for now we'll just think about that these are the complex roots aren't repeated. So if that's the case, our general solution looks like this: some constant a cosine of 3x plus again some constant b multiplied by sine of 3x. Okay, so notice here that it doesn't matter what does for the particular solution. In the particular solution, we could have any coefficients here. We could have any coefficients for cosine of and sine. Okay, that doesn't make the general solution invalid or anything. So the general solution is still the same. Even if you have 1 here, or if you have 5 cosine of 3x here, all of them would lead to this, would point to the same general solution. Okay, all of them would have come from this same general solution. Okay, where we could have any coefficients here and here. Okay, so my point is, well, since we have deduced that far, okay, let's actually deduce the roots also. So the real part of the complex root that we're talking about is 2, and the imaginary part is 3. So plus or minus 3 actually, they come in conjugate pairs. So our we have two more roots. Those are gonna be 2 plus or minus 3. Again, don't know whether they're repeated yet. But let's actually since we should try to work a bit fast here. I'll actually clarify this right now. Okay, right now, we're supposed to have a 7th order differential equation. Okay, so what our goal is in counting and factoring in the multiplicity, or the number of repeats, we should have 7 roots of the characteristic equation total. How many do we have currently? 4. Okay, 4 plus at the very least 1 more, and again at the very least 2 more. So this is a pair. So 4 plus 1 plus 2, 7. We already actually have all the roots. Okay, so none of these are repeated any more times that than what has been shown here. Okay, these two are actually not repeated at all. Okay, these three actually, and this is repeated 4 times, exactly 4 times. Okay, so since we know that, let's write our general solution. So we're done with the real repeated root. Okay, for our distinct real root, the m equals 2, we know that this is gonna be the solution. I already wrote that before. So some constant c5 multiplied by e to the power 2x, and for our complex roots, okay, it's pretty much we already have written that here. It's lambda. Here lambda is our real portion, which is 2, and this is 3. I actually already wrote that. So the other, the last portion of our solution, the one due to the pair of complex roots, it's going to be e to the power 2x, some constant c6 multiplied by cosine of 3x plus the very last constant c7. So we have accomplished our goal of reaching 7 arbitrary constants. That's necessary for this to be a 7th order DE. So c7 multiplied by sine of 3x. Voila, this has to be our general solution. We have reduced this in complete reasonable ways, and we have reached 7 arbitrary constants, same as the order of the differential equation. All right. So the general solution has been written down. What we need to find next is our our differential equation itself. For that, we need to go back to our roots. What our roots are. So our roots are m equals 4, that's repeated 4 times, m equals 2 repeated once, and m equals 2 plus 3i and 2 minus 3i. Both are we just offer once. All 3 of them just offer once each. So m, if m equals 4 is the root, m minus 4 needs to be a factor of our polynomial, right? Characteristic equation polynomial, and this has to have a power of 4. We said that this is repeated 4 times, so this has to have a power of 4. Okay, m minus 2, it's a distinct root, so this is just just to the power of 1. Okay, and then you have m minus, actually I'll use square bracket. So m minus 2 plus 3i, m minus m minus 2 minus 3i, 2 minus 3i. This is also root. All right, this is gonna be equal to 0. This complex portion, I'll just simplify this one. So let's see this thing as a whole. Okay, is actually I hope you have seen how to undo these factorization before expand this. So you have, and you can just do this manually. So it's going to be m squared. What you're going to have in the middle, okay, is negative 2 plus 3i multiplied by m, and also negative 2 negative of 2 minus 3i multiplied by m. The 3i's, they're going to be plus or minus, they cancel. Okay, they're going to cancel, and you have minus 2m and minus 2m. Those are the only ones that are going to remain. So you have minus 4m. Okay, you have minus 4m. You can actually just expand it out normally, and you'll see the same thing. And we at the end minus minus plus for the constant term, and we're just multiplying the conjugates. For that, if you're multiplying them, just find the the magnitude of your complex number. So 2 squared plus 3 squared, that's basically 13. So 13 plus 13. Okay, so this is gonna be this portion. Okay, so our characteristic equation, the factorized form of it, gonna be m minus 4 to the power 4, m minus 2, and this expressed as real factor is m squared minus 4m plus 13. All of this is gonna be equal to 0. And yes, I know what you're thinking, and it's definitely a valid thought. We should really be scared of things like this. It's a very long polynomial. It's gonna take forever to expand this. Okay, it's kind of like a saving grace that this is we can just expand it using the binomial formula. But still, it's still a lot of work. Okay, that's why especially I hope this doesn't come up in your exams or anything. At the most, I hope that this comes in some assignment. So for that, if it's some situation that we can access some calculator, something that can expand. Okay, so some program or some website that can expand, like Symbolab. Okay, so we're just gonna use that. We're actually not gonna do this by hand. Okay, definitely not, if we can avoid that. Okay, so I actually have already done that, and what I get from the expanded form. Okay, the expanded form is gonna be something like this. m to the power 7, 1 multiplied by m to the power 7, minus 22 m to the power 6, plus 213 m to the power 5, minus 1194. I'll actually scroll here. Minus 1194. This is gonna be big. M to the power 4. I'll write it here. Plus 4224 m cubed. Minus 9408. Minus 9408 m squared. Plus 12032 m, and at the very last but not least, we have minus 6656. Okay, and all of this is gonna equal 0. It's gonna equal 0. Okay, so this is our characteristic equation. Actually, I think it's gonna be pretty tiring to write. Even if all that we need to do is just plug in our y's, okay, the derivatives. I think it's still gonna be pretty tiring to write that manually. So I'll just tell you what you need to do. So I think it should be obvious. The powers of m you just replace by the derivative. So m to the power 7, to write the differential equation, it's gonna be replaced by y, the 7th derivative of y. This is gonna be replaced by the 6th derivative of y. This by the 5th derivative of y, and so on and so forth. Okay, so on and so forth. And this is just y. You have a y sticking here. So this is actually your differential equation. This is actually a differential equation. So yeah, we have actually found a differential equation. All right. So the main thing is it is not to see the scariness of these long problems. It's actually as I said, and I hope you're benefiting from this. The main thing is to understand what kinds of solutions arise from what kinds of roots. Okay, I think we should have learned a lot here. The fact that this by itself implies that we have all of this, and the fact that the root is gonna be repeated at least 4 times. Okay, this also just from this kind of like particular form, okay, a very particular function that we're given, we were able to derive a lot, okay, about what the roots are, okay, and how from there what our general solution and our differential equation is gonna look like. So that's really the main goal here. Okay, so one last problem, and this one is because we there's just one case from the 3 that we haven't touched that much. Okay, so that's why I'm doing this one. So we are told that we have a sixth order differential equation on our hands. Okay, and it has a solution. Okay, so let's say that this function we know for a fact is a solution. Okay, is a solution. So x squared e to the power 7x sine of 5x. Now this is interesting. This has all the terms that we could for these equations. We have we have the polynomial term, we have the exponential term, we have the trig term, and the only case that involves all 3 is when we have repeated complex roots. Okay, when we have repeated complex roots. Okay, here like this. So when we have repeated complex roots. So what can we say here? Well, first thing, for those repeated pairs of complex roots, okay, lambda, as I said, it has to be same by definition of being repeated, okay, and they have to be conjugates. So we know for a fact that the 2 complex roots we are talking about, from which this came from, okay, it's gonna be the root is gonna have a real part of 7. Right? It's gonna have a real part, so m is gonna be equal to 7 plus or minus something. So at the very least we know that this is the real part. All right, let's move on. Okay, so the second thing you can notice here is actually the coefficient of x inside the sign. Okay, and this for a fact has to be the same as both of sine and cosine, as we have discussed before. Okay, that cosine or sine cannot actually occur just by themselves. So we also need to have the cosine term with a same degree polynomial as what the sine term is going to have. Anyways, I'll come to that a bit later. But it's a fact that our imaginary part is gonna be mu, right? It's plus or minus mu actually for the pair. Okay, so it's plus or minus mu. So basically plus or minus 5i, plus or minus 5i, plus or minus 5i. Don't know whether this is repeated yet or not. So we need to see that. Okay, so the very last thing is actually what concerns us is x squared. Okay, so we have an x squared here. Now this is again the same logic as before, kind of like the same logic we used here. If there's x squared here, and if we just go back to this, we for the sine term here, okay, so we have it's multiplied by, so all the things are here, all the things are here. So the exponential thing, it's multiplied by the sine, okay. If we just distribute it, so and that's all already we saw that it's already taken care of. The sine term we already saw that already taken care of. The last thing that's multiplied with these, okay, is actually your polynomial, okay. And your polynomial here, it goes up to what, x squared, right? Or at the very least it goes up to x squared. So we know that at the very least, the the roots, the pair of roots that we're talking about, the pair is repeated what, k times. If it's repeated k times, the highest power is gonna be here is gonna be k minus 1. So at the very least, k minus 1 is 2, right? K minus 1 is 2. Okay, so at the very least, the pair, okay, the whole pair, each of the complex conjugate roots themselves, okay, are repeated at the very least k, which is equal to 3 times, okay, at the very least 3 times, okay, at the very least k will be equal to 3. So let's write that down. So this whole pair, okay, or both the solutions individually are gonna be repeated 3 times each, okay, 3 times each. So that actually already accounts for our 6 roots that we're supposed to have. Sixth order DE supposed to give us 6 roots, the characteristic equation, and we've already accounted for that. Okay, each of the conjugates themselves are repeated 3 times, so 3 plus 3. So as a whole, we have 6 roots. Okay, we have 6 roots, counting all the multiplicity and all. So that's taken care of. Now, what's our solution gonna look like? So, well, we can just refer to this. Okay, what we see here, we have the exponential outside. We have the sine polynomial. It's gonna, not just this term, the highest term. It's even gonna go, all the way up to the lower terms. Okay, all the way up to the 0th power of x. And we're gonna have an equivalent, a similar cosine term. Okay, that's we are also gonna have that in the general solution. Okay, in the general solution we also need to have that. Okay, so our general solution is actually gonna look something like this, So y is gonna be equal to, so outside we have e to the power lambda x. We already found the real part is 7. Okay, and it's also, we can be seen pretty easily here, 7x. Okay, your cosine term, first I'll write the sine term, since this is, we can directly see that. So as I said, one thing is, we have verified that, we just a while ago we were saying repeat, the pair is repeated at least 3 times. Okay, at least 3 times. But now we know for a certain, since we have reached the cap, okay, the cap of the solutions. Okay, we have 6 solutions already. We cannot, it's not repeated anymore. So we are gonna have a general, we are gonna go up to x squared. So we're gonna have a general quadratic here. So let's say, some constant a sub 1 plus some constant a sub 2 multiplied by x plus some constant a sub 3 multiplied by x squared. All of this polynomial multiplied by your sine term. We already see this is sine of 5x. So this is sine of 5x. And also, we're gonna have the, similar cosine expression. We're gonna have the similar cosine expression. The polynomial is gonna, go up to the same degree. It's gonna have the same degree. So, it's not very different from what I wrote here. So some constant b1. Okay, actually, since we are working, I actually could have written them as c1, c2. But anyways, we could even just write them, just to see the fact that there are 6 arbitrary. We can write some constant a4 rather than b1, b2, b3. Some constant a4 plus some constant a5 multiplied by x. Some constant a6 multiplied by x squared. Same degree polynomial as the one before, the one above. And this is multiplied by cosine of 5x. Okay, same coefficient of x as this one. Okay, so, and all of this is multiplied, big square bracket, all of this is multiplied by e to the power 7x. So this is our general solution. Voila, we have solved it. This is our general solution. Okay, now what we need to do, this is the very last thing we need to do in this video, is actually just to find our differential equation here. Now, what did I say? We have what are our solutions? 7 plus or minus 5i, that's repeated 3 times. So let's write down what happens when you have 7 plus or minus 5i as the root. So m minus 7 plus 5i, okay, and also m minus 7 minus 5i. Now, this is the pair, okay, solutions. And this is something important that we need to note. I said, the pair or each solution individually, individually they're repeated 3 times, okay? Or, the pair as a whole, this is the more convenient way to write it. You can say if the whole pair is repeated 3 times, so you're gonna have a power of 3 on the whole thing, okay? And that's pretty easy to see now because we have 3 here, 3 here, and you can just bring the power out like that. Anyways, just our exponent rules. So we are just trying to understand things from every angle. But anyways, so this is our this is our characteristic equation, at least the a certain form of it. Okay. Again, I'm just, I know it might be over repeating things, but again, we don't have any more solutions here. So we have reached the cap of the number of roots. So these are our only solution. This is the whole this is our whole characteristic equation. Now all we need to do is expand this. First thing I'd like to do is inside here, I'd like to remove all the complex things. So what we're gonna have is m squared. You can just manually expand this, but it's gonna be minus 7 is minus 14m. The plus or minus 5im. Those things are gonna cancel, and you have basically this multiplied by this. Minuses are gonna cancel. 7 squared plus 5 squared. 7 squared plus 5 squared. That's gonna be a constant. That's basically 74, right? Yeah, that's basically 74. Okay. And this whole thing is cubed, okay? You shouldn't forget that. This whole thing is cubed, and this is going to be equal to 0. This is going to be equal to 0. Now, you can expand this as a trinomial or something like that, but again, I'm not really keen on doing that. So if you can rely on a calculator or some websites, so that's definitely the better thing to do. So I've already beforehand written down the solutions here. Okay, so this one has, it's going to be 1 multiplied by m to the power, so just m to the power 6, okay, minus 42m, minus 42m, not m to the power 5, okay, plus 810 m to the power 4, minus 8960. Again, it's getting hairy as we saw before, so it's minus 8960 m cubed, okay, plus 59940 m squared, okay, minus 22992 m, just m, okay, this is getting long, plus 405224, okay, the constant. This is gonna be equal to 0. This is gonna be equal to 0. This is your characteristic equation. And again, writing all the big constants and just to make the differential equation, it's gonna take time. So I'll just do the replacement here, just like I did before. So m to the power 6, that's basically gonna be replaced by 6th derivative. This is the 5th derivative, and I think you get the idea. This is your differential equation. Voila, we have solved all of this. Again, I'd like you to know that the purpose of this video isn't actually to just solve these long problems. Most of you, I think, are not gonna encounter these sorts of such ridiculously long problems and such. Okay, actually, yeah, you might encounter these types where you need to work backwards. Okay, this is valid. Okay, provided that hopefully your your polynomial in the characteristic equation, you can expand it much simply than some of the things here. But anyways, the thing is, solving the long problems isn't the goal here. Okay, the main goal here is to understand how the nature of the roots relate to the forms of the forms of the general solution. Okay, and to if we have the nature in the roots and how many times they're repeated, we can go to the general solution. If you're given some particular solutions, from that we should be able to go to our differential equation and our general solution. So that's the main goal. So understand this, this whole thing, the solving nth order linear homogeneous ODEs with constant coefficients. So understanding this in its entirety. So I hope this video has contributed to your understanding, so to reach the apex, okay, so as far as possible. So if you like this video, please do subscribe, please leave a like, and I'll see you next time and study smart.